a queue of pages that are currently resident. And so this is physical, this lives in physical memory. So your VM object knows what is in memory and what's not in memory. Shadow object is actually another VM object. If it gets weird or complicated, tell me. I hope not. So shadow object is another VM object which gets created when you do copy and writing. So to begin with, you have one VM object. And let's say you copy and write share it with somebody else. So to begin with, there's just one VM object, and somebody actually writes to it. So what the kernel will do, it will create a shadow object, which will contain the pages that you just modified. And it'll attach them such that the person who modified, when the kernel is accessing things on their behalf, first you will see in the shadow object to see if there's a new, it's basically common sense stuff. And as you keep writing more, you will have these chains of these shadow objects, which can collapse if necessary. And then we have this interesting thing called a memory object, which is really the portal to where the memory comes from. And a memory object is implemented as a mock port. So a quick aside on mock ports. I think the simplest way to understand them, and it's kind of important to understand them because they underlie all mock IPC, and IPC underlies all mock operation, and mock underlies OS X. A mock port is kind of like a Unix, like a BSD socket, except that it's not really for networking. It's optimized for the local case. So there's a message queue in the kernel, and you can do asynchronous message sending and receiving. But the special property is that there's only one task. Technically, any thread within the task can receive messages on a given mock port. And this property is known as the task has received writes to the port. But you can have multiple senders. So why this mock message thing and this port thing is important and actually really, really useful for people like us is because all system activity happens through these things. For example, your window manager. If you're talking bottom line, your window manager represents each window as a mock port. So if you wanted to do some funky stuff with a window, I mean, at some level you were talking to a mock port. And then the other kind of interesting property is that the kernel also is a task. And mock APIs do not really distinguish between, when you do IPC, it doesn't matter if you're sending it to the kernel or user, because the kernel is the arbiter. But you can modify the kernel like you would modify a user task. So for example, if I want to allocate some memory in the kernel, I can do it exactly the same way as I would do it in user space. If I want to set the instruction pointer of a given thread in the kernel to something I want, given the right privileges, I can do that very easily, but exactly the same way I would do it in user space. So this uniformity is both good and bad, but for most of the stuff I like to do, it's actually very good. So given that we know what a mock port is, memory object is just a mock port. So I told you about receive writes and send writes. So who owns the receive write to this port? Well, that's the pager. And pager is just what it sounds like to be. Pager is the guy who actually gets the memory from wherever it lives. So now let's look at the memory object in more detail. I think this picture sums it up. So where could memory come from? Well, it could come from many places, right? It could come from a file system. If you mmap files like all dynamic shared libraries and whatnot, they're memory mapped. So they can come from the file system. And that's handled by what's called a vnode pager in macOS X. Memory could come from a device like a frame buffer. That kind of memory is handled by the device pager. Memory could also come from nowhere, because if you malloc, it comes from nowhere. So that's anonymous memory, but when you want to write it out, it has to go somewhere. So normally it goes to the swap space. So the pager that handles that is the default pager. So macOS X has at least 3 types of pagers, the ones that I just mentioned. Now why do I say at least? Well, before I answer that, in this picture, you can do something like this. Meaning you can just interpose a new pager, and you can start like siphoning memory or feeding memory if you want, pretty much using interfaces. So why this thing is kind of cool, because you're not really hacking anything if you're using interfaces. Like Apple doesn't want you to use the interface, and they're not documented, but still, all this can be done with just the supported stuff. So, given this picture, one of the things Apple does is what's called Apple protected binaries. So this is one thing I really like about Apple, which is that they're very pragmatic. If they're solving a problem, so they have as good engineers as anybody else. So somehow they know, for the most part, where to draw the line. They're not going to solve the problem until, like those who are working on it like die of frustration, and it's like you have to go to the academic edge case that it cannot be broken in any circumstances, so solve it until then. They don't do that. They actually solve it for most of their users. And so this is a good example of that. So if you look at the Finder, for example, the Finder binary on your system, it's an Apple protected binary. What that means is it's just encrypted. And we talked about AES encryption a little before. It's encrypted using AES. And yeah, I mean, there's got to be a symmetric key somewhere. So with the pager picture, all this VM knowledge that we just gained, essentially this is what they do. So you have an encrypted binary which lives on disk. When you're reading, it goes through the vNode pager as it normally would. The numbers are kind of backwards, actually, if I start from here, but it's okay. So they just set a special bit in the Mako header of the binary which says, hey, this is an Apple protected binary. You can clean that bit and you'll see that it just said false. So it'll go to the pager. The exact vsystem call implementation identifies this bit, and what would normally happen is that, the first page is not encrypted. Actually, the first 3 pages are not, because they got to identify what's going on. So normally, you would start mapping pages in as you try to execute a binary. So the moment they see that it's a protected binary, all they do is that they instantiate something called an Apple Protect pager, and they swap the memory object port so that the original VM object sees the new one, and this guy has the old one. Very simple. I mean, there's no tricks here. So all that's happening is that this guy reads protected, encrypted data from the file system. It decrypts on the fly. And it's a trivial pager because this stuff is never going to be paged out. You're not going to write to it. You don't have the keys. You shouldn't write to it. So that's all. I mean, that's one of the things they do. And oh yeah, there's got to be keys somewhere. So yeah, so there's keys somewhere, and the keys come from somewhere, and that's how it works. And while we're on the topic of VM, before we switch context again, there's this interesting experiment you can do which actually highlights multiple things at the same time. So what are you doing here? You're printing like some address as a string from the end of your address space, minus 16 times, so like last few pages. And if you compile it and run it, so what do you see? So what is this thing doing in your address space, first of all? I'm talking about every process's address space. Like you can write a new program and you'll see it there too. Well, first of all, this is a feature. Well, not the poem. I'm talking about the fact that things are mapped in your address space. The feature is that, in there, like, have you ever wondered, I don't know if you've experienced it yourself, but I've certainly heard a lot of Apple users say that, Apple has this wonderful way of making every release faster on the same hardware. So there's no magic. They must be doing something right. So they do some things which actually help. Some other things don't help. I think the users are just hallucinating. But no, but they do some things that actually help. And one of the things is that, actually we don't have to go into that's a whole new topic. But the way this feature works is that they map shared libraries into the same addresses, virtual addresses in every process. So, which means that C library is going to be mapped into the exact same virtual addresses in every process. Well, forget about the C library. Let's say it's some weird, like, funky Apple library that nobody uses, but that's going to be mapped into the same space too. So what if you need that virtual memory and you're not even using that library? Well, tough luck. But it worked for the most part. I haven't heard people complain that I ran out of virtual address space. I really wanted that memory and couldn't get it. Okay, so in that pager picture, much of the decryption code lives in a kernel extension called Don't Steal macOS 10. And the poem is put there by that extension. So this is like a salt. Like they verify that everything is fine and dandy. And if it is, they say let's just put it in every address space at this address. And it's kind of like a little flag that says it's no big deal, which says everything is okay. You can put it there yourself. So let's switch context again. I think when I was going through the past year's proceedings or the talks that were held here, I think most people should know what these are, how they work, what capabilities do they have. So I'll try not to talk too much about these things because I don't want to be redundant. But for what it's worth, 20 million of these shipped last year. And it's expected that by 2010, there will be about 250 million of these deployed. So whatever these things are, good or bad, they're out there. And like I said earlier, Microsoft's Palladium had a lot of bad vibes to it, and it sounded quite draconian. And they were not even using the TPM, for God's sake. They were using their own chip. But the TPM actually got a lot of, and they're valid concerns. Not all of it is invalid. But, so first of all, so it's in many Intel Macs. It's not in all Intel Macs. We'll come to that later. But in machines that do have this, it just sits on the LPC bus. It was actually not required to be on the LPC bus earlier. But the new specification of the TPM 1.2, it requires it to be on the LPC bus. I understand most people know but actually that's not even important. Now what's inside it? I think the easiest way to think of it is that it's like a smart card, except you carry a smart card and this is on your motherboard. And in fact, if you see what chipset is inside, what embedded stuff it's running, it's actually running the same stuff as a smart card would. Except it's like when the company who manufactures this also makes the smart card, so there's a small production difference. But it's running a lot of the same things a smart card would. Stuff like this. So there's a microcontroller. Which thing doesn't have a microcontroller? There's a few types of memory, both volatile and non-volatile. And there are some functional components, lots of cryptographic stuff, some of which it exports, some of which it does not export. For example, some people I've talked to, they kind of think that it's like a crypto accelerator. It's not, and that's for good reason. It's because they want it to be cheap and they want to be able to export it. So this is not a crypto accelerator. It does do both symmetric and asymmetric cryptography, but the symmetric stuff is internal only. It's not even exposed. So we will see some of these components later on. So that was like an internal view, but from a programming standpoint, what can you do with it? So if you're a programmer who wants to access this, well, you can use the functional units to do some kind of signatures. You can get like really nice random numbers. You can get like monotonic counters. It has a bunch of keys. We will come to the stuff that actually matters to us in this talk, but it actually has storage storage now that you can use for anything you want. It's very small, but it has some storage.